Normally, when you hear about quantum in pop culture, you might think it's fantastical or abstract or confusing. But here, we actually get the ability to play with quantum mechanics. We can understand its properties. We can use it as a tool to solve problems. In 2019, our first significant step was to show that this technology is real. We ran a very specialized algorithm on one of our prototype quantum computers in 200 seconds that would have taken the world's largest supercomputer 10,000 years. Since then, we've charted a course to make these computers large-scale and generically useful. And we're excited to give you a peek into our lab to show you what quantum computing is all about.
So, when people think of a quantum computer, they often think of the big dilution fridge and the beautiful chandelier. What is actually doing all the processing is this little tiny chip all the way at the bottom, and that's the quantum processor.
Classical computers use binary bits, which are just zeros and ones. However, quantum bits have that same bit be some state in between the 0 and the 1. And that state, when you start adding arrays of quantum bits, gives you exponentially more computing power than you have with classical bits.
We make qubits by putting aluminum on silicon in a special pattern, and that special pattern is our qubit.
We make that quantum processor in-house here in Santa Barbara, which consists of a clean room because it's critical that we don't have anything that would cause them to lose signal.
As we continue to grow the amount of qubits on our wafer, we can't shrink our qubits because they're defined by the size of the capacitor. So we have to make our processable area larger and larger.
And that's where we start getting creative.
Normally, we kind of paint a picture for people of what packaging is, because it's a very broad, vague term. Where we specifically live in that spectrum of electronics packaging is the bridge between the quantum processors and these large cryostats that live outside. We have all these requirements being light tight, able to thermalize to really cold temperatures, and shielding all this stray radiation to give the qubits an environment where nothing is interacting with them from the outside world.
Cold, dark, and quiet.
Cold, dark, quiet.
Yeah. Okay, so here's an example of one of our packages where our qubits live, and signals have to connect to it all the way to the processor. Yeah, you can't see it here, but we use a very thin piece of wire. This is 18 microns in diameter to connect from the circuit board to the chip. And human here is about 80 microns in diameter, so our wire is about a fourth.
It's very tedious to physically thread it into the needle of the machine, which Anthony is really good at.
I did it.
And I'm really bad.
I got the shot.
The cool thing about this technology is that we're designing and building and testing the next generation of electronics packaging, or quantum packaging rather. Nobody else is doing what we're doing, which is why it's hard.
Wow, inspirational.
I just fired myself. I gotta get to work.
As I like to say, I have the coolest job. That's because I actually make some of the coldest spots in the universe.
So you're probably wondering why we need this whole machine to only have a small chip. And that is because qubits rely on something called superconductivity. And in order to have that in the chip, you need very, very cold temperatures.
This dilution refrigerator is made up of two main cooling loops. You have the pulse tube, which is making all the wonderful chirping noises. And then you have the dilution core made up of a series of plates that the farther down you go, the colder you get. We start at room temperature, 50 Kelvin, 10 Kelvin, 3 Kelvin, which is outer space now for a reference, 1 Kelvin, 0.1 Kelvin, 0.01 Kelvin. And this here below the plate is where we actually mount the quantum processor. Literally the coldest places in the universe.
All this messy wiring over here is basically just to communicate with the qubits. You have to send them very particular signals. So part of my job is to figure out what are the signals to have these qubits do the things that we want them to do.
Okay, so you've seen us make qubits, package qubits, put it into a fridge, close that fridge. We're gonna cool down the fridge, but we still don't even have a quantum computer. We're gonna need to control algorithms on it eventually. So to control algorithms, we're gonna need a very specific arrangement of quantum gates, operations, and measurements.
all of these racks and all these wires that come out of those racks are used to generate the waveforms that we use for control. For example, in blue, you have something that is a microwave gate, and in yellow, you have something that is a DC gate. And these are different types of operations that we would put down on our qubits. And you'll see that we're changing sort of the size and the shape of those waveforms, and that really is what the process of calibration is. You're gonna do several of these different kinds of experiments, and that's a sequence of calibrations that eventually get you to the algorithms that you wanna run.
Most of these cables are sending information in. A few of them are giving us information out. You can think of that almost as if a sound wave is bouncing off the wall. It's gonna come down, echo off, and return, and it's that final answer that we're actually after.
What you just saw was a glimpse into the birth of an entirely new technology, one that has the capability to solve problems that would otherwise be impossible in chemistry, machine learning, material science, and medicine. We're making rapid progress, and we'll be excited to tell you about our advances in quantum hardware and cutting-edge algorithms as we continue the journey towards our next milestone.